Children, we have done with the fourth unit of class 12th chemistry, that is chemical kinetics. Let me take up some of the numerical on chemical kinetics. Number 1, express the rate of the following reactions in terms of concentration of reactants and products. Number 1, PCl5 giving rise to PCl3 plus Cl2, nitrogen dioxide giving rise to nitric oxide plus oxygen. So in this numerical, you need to express the following reaction, a rate of a reaction in terms of concentration of reactants and products both. Let me solve. Solution. Children, let me take up the first one, that is PCl5 phosphorus pentachloride. On decomposition, you are going to get phosphorus trichloride plus chlorine gas. Now how do I write the rate of the reaction? Look at here, rate is equal to, so this is what the reactant, these are what the products, is it not? And you learned that while writing the rate of a reaction for reactant, I need to use a minus sign because the concentration of the reactant keep on decreasing and it becomes a minus, and the rate cannot be a negative quantity, it should be positive. That is why I need to put negative sign here. Look at here, minus D concentration of PCl5 upon dt. Hope you got it? Is equal to, these are the product, the concentration product keeps on increasing and is a positive entity. Now look at here, D concentration of PCl3 upon dt, that is equal to, you can say plus also, no problem, plus D concentration of Cl2 upon dt. So this is how you need to write the rate of a reaction for the first reaction, wherein phosphorus pentachloride decomposes to give phosphorus trichloride and chlorine gas. Second one, 2NO2 nitrogen dioxide decomposes to give 2NO nitric oxide plus O2. Children, in this case, rate is equal to minus, because you are writing for the reactant, 1 by 2 molar concentration of NO2 upon dt, that is equal to plus 1 by 2 D molar concentration of nitric oxide upon dt, that is equal to plus D molar concentration of oxygen upon dt. Children, one of the simplest numerical. You may not get this kind of a numerical in board examination. Maybe get in terms of competitive examinations like NEET or JEE or something like that. Okay, hope you understand that. Let me go for the second numerical. Let me go for the second numerical for you, children. Ammonia and oxygen react at very high temperature as 4NH3 plus 5O2 giving rise to 4NO plus 6H2O. In an experiment, the rate of formation of a nitric oxide is 3.6 into 10 to the power of minus 3 mole per liter per second. Calculate A, rate of disappearance of ammonia, B, a rate of formation of water. Children, let me solve this numerical for you. Remember, before finding out the rate of disappearance of ammonia and rate of formation of water, let me write differential rate equation for this reaction. Look at here, solution. So let me write the equation again, 4NH3 plus 5O2 giving rise to 4NO plus 6H2O. Let me write the differential rate equation. Rate is equal to minus 1 by 4 d into molar concentration of ammonia upon dt, that is equal to minus 1 by 5 d into molar concentration of O2 upon dt, that is equal to plus 1 by 4 d molar concentration of NO upon dt, that is equal to plus 1 by 6 into molar concentration of H2O upon dt. Is it not? Now let me take up the A part. What is that? Rate of disappearance of ammonia. Is it not? Children, look at here. The rate of disappearance of ammonia is equal to a rate of formation of nitric oxide. Is it not? Look at here. The rate of disappearance of ammonia is equal to the rate of formation of nitric oxide rather. Look at here, how to write that? Rate of disappearance of ammonia is equal to, directly I'll write, a rate of formation of nitric oxide. Now children, why did I write like that? Look at here. Numerical coefficients same here. Numerical coefficients are same. So that is why rate of disappearance of ammonia is equal to rate of formation of nitric oxide. Now in that case, you know that rate of formation of nitric oxide is given here. It is equal to 3.6 into 10 to the power of minus 3 mole per liter per second. That means the rate of disappearance of ammonia is equal to 3.6 into 10 to the power of minus 3 mole per liter per second. Hope you got it. Let me go for the second part of this numerical, that is rate of formation of water. Look at here. A rate of formation of water can be is equal to a rate of formation of nitric oxide. The same thing I'll write here, because I know the value of rate of formation of nitric oxide, that is equal to 3.6 into 10 to the power minus 3 mole per liter per second. So what I write here, a rate of formation of water is equal to rate of formation of nitric oxide, NO. Now I know the expression here. What is the expression for this? Is it not? It is 1 by 6 d molar concentration of H2O upon dt, that is equal to, what I write other side, 1 by 4 molar concentration of NO upon dt. Is it not? Now children, look at here. d H2O upon dt is equal to 6 by 4 into this value, you know this, how much? 3.6 into 10 to the power of minus 3. Is it not? Look at here, 4 ones are 0.9, right? That is equal to 5.4 into 10 to the power of minus 3 mole per liter per second. So that is how you need to solve the numerical. Hope you understand about this numerical. Let me take up one more numerical for you. Children, let me take up the third numerical. For an elementary reaction, 2A plus a B giving rise to 3C. The rate of appearance of C at time t is 1.3 into 10 to the power of minus 4 mole per liter per second. Calculate at this time A, rate of a reaction, B, rate of a disappearance of A. Children, as usual, first you need to write the differential rate equation for the above reaction. Let me solve. Solution. So differential rate equation, I write the reaction 2A plus B giving rise to 3C. Is it not? Now rate, differential rate equation, rate is equal to minus 1 by 2 D into molar concentration of A upon dt, that is equal to minus D molar concentration of B upon dt, that is equal to plus 1 by 3 D molar concentration of C upon dt. So this is what? Differential rate of a reaction. Children, let me take up the first one, A, that is a rate of a reaction. The rate of a reaction. For finding the rate of reaction, can I take any of the thing? But in this case, what I do, I'll take this one because they are given here a rate of appearance of C. That is why it is better if I take this for finding the rate of a reaction. Children, let me write a rate is equal to 1 by 3 D molar concentration of C upon a dt. Now 1 by 3, so look at here, this value they are given here. How much? It is 1.3 into 10 to the power of minus 4. Is it not? Now if you simplify, you are going to get 0.434 into 10 to the power of minus 4 mole per liter per second. Or I can also write by reshuffling the decimal place, rate is equal to 4.34 into 10 to the power of minus 5 mole per liter per second. So this is the first part of finding the rate of reaction. Let me go for the second part. What is that? Rate of disappearance of A. A rate of disappearance of reactant A. Children, in this case I need to take this, is it not? Now you know that a rate of disappearance of A is equal to a rate of appearance of C. Is it not? What do I do? Look at here, a rate of disappearance A is equal to a rate of appearance of C. Now look at here, this is what the rate here. So you should neglect minus sign there. 1 by 2 into D concentration of A upon a dt, that is equal to 1 by 3 into concentration of C upon dt. Is it not? Now children, I need to find out disappearance of A, right? Now 2 by 3, because this 2 I will take it here, 2 by 3 into this value, you know that how much? It is a 1.3 into 10 to the power of minus 4 mole per liter per second. So I'll write here 1.3 into 10 to the power of minus 4 mole per liter per second. Children, if you simplify, you are going to get 0.8 838 into 10 to the power of minus 4 mole per liter per second. Or you change the decimal place, children, you are going to get a rate of disappearance of A is equal to 8.38 into 10 to the power of minus 5 mole per liter per second. This is how you need to solve any numerical where you are asked to find out a rate of a given reaction. Hope you understand that. Let me take up one more numerical. So let me take up the next numerical for you. Fourth one. Calculate the overall order of a reaction which has a rate expression A. Rate is equal to K into molar concentration of A raised to 1 by 2 into molar concentration of B raised to 3 by 2. B. Rate is equal to K into molar concentration of A raised to 3 by 2 into molar concentration of B raised to minus 1. Children, one the very simple numerical. You have learned that order of a reaction is defined as sum of the powers to which the concentration terms are raised in a rate law expression. Use the definition to find out the order of a reaction. Let me solve. Solution. A rate is equal to K into molar concentration of A raised to 1 by 2 into molar concentration of B raised to 3 by 2. Now, order. Children, look at here. 1 by 2 plus 3 by 2. Now that is equal to, if you simplify, 8 by 4, that is equal to 2. So order is equal to 2. So second order reaction. Let me go for the second part of this. A rate is equal to K into molar concentration of A raised to 3 by 2 into molar concentration of B raised to minus 1. So order is equal to, it is 3 by 2, sorry, 3 by 2 minus 1. Is it not? If we simplify, 3 minus 2 upon 2, that is equal to plus 1 by 2. So order is equal to plus 1 by 2. So this is how you need to solve the numerical or to find the order of a reaction. Children, let me take up the next numerical for you. Write the units of a rate constant for nth order reaction. Deduce from this the units of rate constant for off order reaction, the second 3 by 2 order of a reaction, and third order reaction. So solution. First I need to write for nth order reaction. Children, for nth order reaction, now we have K is equal to mole per liter 1 minus N per second. Is it not? Now N is nothing but the order of that reaction. In that case, let me solve for the first one, of order reaction. That means order is equal to 1 by 2, that is N is equal to 1 by 2. Is it not? Now K is equal to mole per liter 1 minus 1 by 2. So per second. In that case, mole per liter 1 by 2 per second. Is it not? So mole 1 by 2 liter minus 1 by 2 per second. So this is the unit of rate constant for off order reaction. Now second one, look at here, for 3/2. Now how do I write? So order is equal to 3/2. In that case, K is equal to mole per liter 1 minus N per second. Is it not? Mole per liter, 1 minus 3/2 per second. So mole per liter, so it will be 2, I'll take it as 1, 2 minus 3/2 per second. That is equal to mole per liter. Children, this will be minus 1/2 per second. So mole of minus 1/2, liter 1/2 per second. Hope you're following. Third one, we have, what is that? Third order reaction. Third order reaction. That means order N is equal to 3. So K is equal to nth order, mole per liter 1 minus N per second. Is it not? So mole per liter 1 minus 3 per second. That is equal to mole per liter 1 minus 3 is equal to minus 2 per second. So mole minus 2 per liter. Now it will be minus 2 minus plus second. So this is how you need to find out the order of a rate constant for different order of reaction by using the expression for nth order of a reaction. Let me take up the next numerical for you. The rate law for a reaction A, B and C has been found to be, rate law expression, rate is equal to K into molar concentration of A into molar concentration of B into molar concentration of C raised to 2. How would the rate of a reaction change when A, concentration of C is doubled, B, concentration of A is odd, that means reduced to off, C, concentration of both B and C are doubled, and D, concentration of A, B, C are tripled? Very simple numerical and frequently has been asked in the board examination as well as in competitive examination also. Let me solve. Let me consider the initial concentration of ABC as, look at here, concentration of A is equal to A mole per liter, concentration of B as B mole per liter, concentration of C as C mole per liter. Children, in that case, how do I write the rate expression? Look at here, rate is equal to A, K into A, B, C square. Right? Hope you got it. Now let me take up the first part of the numerical. When the concentration of C is doubled, concentration of C is doubled. That means C, concentration of C is equal to 2C. Hope you got it. Is it not? Now the rate is equal to K into A, B, C square. Right? Now look at here. K into A, B, C. In place of C, I'll put 2C whole square. Now 4K A, B, C whole square. That means the rate of a reaction is increased by 4 times when the concentration of C is doubled. Hope you understand that. So rate of reaction is increased by 4 times. Let me go for the second part. B. What is that? Concentration of A is odd. That means reduced to half. Look at here, concentration of A is odd. Refers to reduced to half. Now look at here, concentration of A, I'll take it as what? 1 by 2A. Hope you got it. Concentration reduced to half. Initial concentration reduced to half. So in that case, a rate is equal to K into ABC whole square. Now K, A how much here? So 1 by 2 ABC square. That is equal to 1 by 2 into KABC square. That means, children, remember, when the concentration of A is reduced to half or odd, the rate of a reaction is also reduced to half. Hope you got it. Now let me go for the third one, C. Look at here, third one, concentration of both B and C are doubled. Concentration of B and C are doubled. So that means concentration of B is equal to 2B and concentration of C is equal to 2C. Now substitute the value here. Now rate is equal to K into ABC square. Now look at here, K into A as it is. In place of B, it is equal to 2B. In case of C, it is 2C whole square. Look at here, children, 2 into 4, 8. 8 K A B C whole square. That means a rate of a reaction is increased by 8 times when both the concentration of B and C are doubled. Now the last one, D. What is that? When the concentration of A, B, C are tripled. Now look at here, A, B and C are tripled. Concentration tripled. In that case, look at here, concentration of A is equal to 3A, concentration of B is equal to 3B, and concentration of C is equal to excuse me, 3C. Now I'll write a rate is equal to, look at here, K into A into B into C whole square. Now K, look at here, A is equal to how much here? I'll write here, into 3A, B is equal to 3B into C is equal to 3C whole square. Is it not? So 9 3s are 27, 27 3s are 81. 81K into A, B, C whole square. Children, the rate of a reaction is increased by 81 times when the concentration of A, B and C are tripled. Let me go for the next numerical. A reaction is of second order with respect to a reactant. How is the rate of a reaction affected if the concentration of reactant is first part doubled, second part reduced to half? Given R is equal to molar concentration of A raised to 2. If molar concentration of A is equal to A, then R is equal to K into molar concentration of A raised to 2. Children, let me solve this numerical for you. Solution. Now, we know that a rate law expression, a rate is equal to K into molar concentration of A raised to 2. Is it not? In this first part, when the concentration of a reactant A is doubled, that means it becomes 2A. Is it not? Now, a rate is equal to K into 2A whole square. That is equal to 4KA square. Children, in this case, when the concentration of the reactant doubled, the rate increases by 4 times. Second one, when the concentration of reactant is reduced to half, children, in that case, look at here, concentration of A is equal to 1 by 2A. Is it not? Now look at here, we know that a rate is equal to K into 1 by 2A whole square. Now that is equal to 1 by 4KA square. That means when the concentration of a reactant A is reduced to half, the rate of a reaction decreases to 1 by 4th. So that's how you need to solve the problem. Let me take up the next numerical for you. How will the rate of a reaction change when A0 is doubled or tripled for 0 order reaction and second order reaction? Children, again it's very simple numerical. Let me solve. Now what do I do? First I'll see when A0 is doubled, and later I'll take up when A0 is tripled. Children, under that, first one I'll take up for 0 order reaction. 0 order reaction. Remember, the rate of a reaction remains unchanged for a 0 order reaction, whether the concentration is doubled or tripled. So here what I write? A rate of a reaction for 0 order reaction remains unchanged. And the second part for second order reaction. For second order reaction. Look at here. If I want to write the expression, a rate law expression for second order reaction, I can write a rate is equal to K into A to the power 2, because the second order reaction. Now what do they say here? A0 is doubled. A0 is doubled. Now look at it, children. What I do? K to 2A whole square. Is it not? Now you are going to get 4KA square. That means for second order reaction, when the concentration of A0 is doubled, the rate increases by 4 times. Similarly, let me take up the other side also. That is, when A0 is tripled, under that for 0 order reaction. Children, as I said, 0 order reaction are independent of initial concentration. That means the rate for a 0 order reaction remains unchanged whether it is doubled or tripled. So here also the rate remains unchanged. And that second part for second order reaction. Now how do I write the rate expression? Rate is equal to K into E to the power of 2. Children, what do they say here? When the A0 concentration is tripled, now what I do? K to 3A whole square, that is equal to 9K square. Now when the concentration of A0 is tripled for a second order reaction, the rate increases by 9 times. So this is how you need to solve the numerical on the 0 order as well as second order reaction when the concentration of A0 is varied, doubled or tripled. Let us take up next numerical. Identify the order of a reaction from each of the rate constant. K is equal to 2.3 into 10 to the power of minus 5 liter per mole per second. Second one, K is equal to 3.1 into 10 to the power of minus 4 per second. K is equal to 9.3 into 10 to the power of minus 4 mole per liter per second. Children, and how to identify the order of reaction just by seeing the constant value, rate constant value? Children, you can easily identify. How? By seeing the units associated with each of the rate constant value. Now look at here, the first one, liter per mole per second. Children, it is for second order reaction. So this is a second order reaction. Now look at here, per second. Per second is a unit for rate constant for first order reaction. First order reaction. Mole per liter per second is for the zero order reaction. Zero order reaction. Children, just by seeing the unit of a rate constant, you can easily identify whether it is belongs to first order, second order, or third order, etc. Hope you got it. So first one is of second order, second one is of first order, third one is of zero order. How did you identify? Just by seeing the units of rate constant. Hope you got it. Let me go for the second numerical under this. A reaction is of a second order with respect to a reactant. How is the rate of a reaction affected if the concentration of reactant is reduced to off? Continuation is there. What is the unit of a rate constant for such reaction? Children, again it's a very simple numerical. Let me solve. Solution. What they say here? A reaction is of second order with respect to a reactant. Now let me write a rate law expression for second order reaction. How do I write? Look at here. A rate is equal to K into molar concentration of A. Let the reactant be taken as A. Now raised to 2 because it is a second order reaction. Hope you got it. Now what do they say here? How is the rate of reaction affected if the concentration of reactant is reduced to off? That means the concentration of A is reduced to off. Now in that case, look at here, K into of A whole square. Right? Now I simplify. This will be 1 by 4 K A square. Children, that means the rate of a reaction is reduced to 1/4 when the concentration of A is reduced to off. Hope you got it. Now second part, what is that? What is the unit of rate constant for such a reaction, like second order reaction? Is it not? How do I write that? Look at here please. You know that for nth order, how do I write? K is equal to mole per liter 1 minus n per second. So this is what? For the nth order. Now mole per liter, and n value is what much here? It is 2. Why? Because the second order reaction. Now 1 minus 2 per second. So mole per liter minus 1 per second. Look at here. Mole inverse 1 liter per second. Or you can write liter mole inverse second inverse. So this is what? The unit of rate constant for second order reaction. So you can verify here. Look at here. The same. Right? Hope you got it. Again, it's a very simple numerical. So you will get 2 marks if you solve this numerical. Children, let me take up one more very important numerical. The decomposition of N2O5 at 318 Kelvin according to the following equation follows a first order reaction. N2O5 giving rise to 2NO plus of a molecule of oxygen. The initial concentration of N2O5 was 1.24 into 10 to the power of minus 2 mole per liter, and that of after 60 minutes was 0.20 into 10 to the power of minus 2 mole per liter. Calculate the rate constant of the reaction at a 318 Kelvin. Given the log value of 6.2 is equal to 0.7924. Even if they do not give log value, you are supposed to find out, and you know how to find the log value as well as anti-log value, is it not? Now let me solve this numerical. Children, let me list down whatever the data given in the numerical. Given data. What do they say? Yeah, it is a first order reaction, is it not? And the initial concentration of N2O5 is given. That means R0 is given. R0 is equal to 1.24 into 10 to the power of minus 2 mole per liter. Is it not? And T is given. Is it not? How much T? Yeah, T is equal to 60 minutes. And after 60 minutes, that means concentration of R is also given, that is equal to 0.20 into 10 to the power of minus 2 mole per liter. Hope you got it. Now what are they asking? They are asking to find out the value of K for this reaction. Children, once you write the given data in the numerical, now you need to go for finding the value of K here. And one more hint is given, children. Here it is a first order reaction, and you know the expression for first order reaction. Look at here. Now K is equal to 2.303 upon T into log of R0 upon R. So this is what the expression for first order reaction, is it not? That already learned that. Now let me substitute the value 2.303 upon T. T is how much here? It is 60 minutes, right? As it is 60 minutes into log of R0. What is the value of R0? R0 is equal to 1.24 into 10 to the power of minus 2 upon R value is given here, is it not? After T 60 minutes, R value is given, it is 0.20 into 10 to the power of minus 2. Now if I simplify, this will be, I think, 6.2. Now let me write. So this, if you simplify this, you're going to get 0.0383 into log of 6.2. Now 0.0383 log 6.2 is given here 0.7924. Now if you simplify, you are going to get 0.0303 now per minute. Why per minute? The unit of rate constant for first order reaction is per minute in this case. Usually take it as per second, but in this case it is per minute. So this is what the value of rate constant for the above reaction, where N2O5 decomposes to give 2NO plus of a molecule of oxygen. Let me take up one more numerical, which is very important as far as the board examination is concerned. A first order reaction has a rate constant 0.0051 per minute. If we begin with 0.10 molar concentration of a reactant, what concentration of a reactant will be left after 3 hours? Children, again they are saying first order reaction. There's a hint here. Now let me solve this numerical. So, given data. So whenever I start solving the numerical, read it 2 times the numerical so that you can understand the numerical in a better manner. So what they given here? K is given. How much? 0.0051 per minute. What else is given? Initial concentration is given, children. R0 is equal to 0.10 molar concentration. What concentration of reactant will be left after 3 hours? So T is also given, children, that is 3 hours. Now remember, as the rate constant is in the minutes, I need to convert this hour into minutes. So 3 hours, 3 into 60, that is equal to 180 minutes. Hope you're following that. And what are they asking here? What concentration of reactants will be left after 3 hours? That means you are supposed to find R. Right? Now what is the int here? It's a first order reaction. How to write? Look at it, children. K is equal to 2.303 upon T into log of R naught upon R. Is it not? K value is given. How much it is? 0.0051, 2.303. T is given. How much it is? 3 hours or 180 minutes. And log of R naught is given. R naught is how much here? 0.10. 0.10 upon R. What you are supposed to find out? You are supposed to find out R. Right? Now log 0.10 upon molar concentration of R is equal to look at here, 180 into 0.0051 upon 2.303. Hope you got it, children. If you multiply, you are going to get a 0.918 upon 2.303. So that you if you simplify, you are going to get 0.3986. So this is what log 0.10 upon R. Right? Now what I do? I keep it as it is, 0.10 upon concentration of R. Log I will take other side, it will become anti-log, 0.3986. So if you find out the anti-log of this, and you know how to find out the anti-log also, and you're going to get 2.508 approximately. Right? So now what I do? So this is what? 2.508. Now what I do? I want R value. I revert it. In that case, 0.10 upon 2.508. So if you simplify, you are going to get 0.0399 m, or approximately you can say that 0.4 molar concentration. So that is how you are supposed to solve the numerical. Hope you got it. Now how did I get this? Children, look at here, 0.10 upon molar concentration of R, that is equal to 2.508. I invert it. How do I do that? Look at here, R upon 0.10. In that case, 1 by 2.508. Is it not? Then R is equal to 0.10 upon 2.508. If you simplify, you are going to get 0.0399 m, approximately 0.4 molar. Children, let me take up the next numerical. The initial concentration of HCO2H, which is nothing but HCOH, formic acid or methanoic acid, is a first order reaction with a rate constant of 2.4 into 10 to the power of -3 per second at a certain temperature. Calculate how long will it take 3/4 of initial quantity of HCOH for decompose. Given log 4 is equal to 0.6021. Children, remember, if they do not give the log value, you are supposed to find out the log value by using log table book. Now let me solve this numerical for you. Solution. So before solving this numerical, we have to list down what are the things which are given in the numerical. So given data, so rate constant is given, that is equal to 2.4 into 10 to the power of -3 per second, and that's all, is it not? Now children, what do they say here? How long will it take 3/4 of the initial quantity of HCOH for decompose? That means, look at here. Now I write R is equal to R naught minus 3/4, is it not? 3/4 of R naught. Hope you're getting that. Right? Now I simplify. So 4 R naught, so that means 4 R naught minus 3 R naught upon 4. So that is equal to R naught upon 4. Right now? Now what else is given here? Log 4 value is given. Log 4 is equal to 0.6021. Now one hint is given. What is the hint here? First order reaction. It is a first order reaction, and you know first order reaction K is equal to 2.303 upon T into log of R naught upon R. Right? Now I reshuffle. T is equal to 2.303. Now K into log of R naught upon R. Children, look at here. 2.303. K value is given, is it not? It is 2.4 into 10 to the power of minus 3 per second into log of R naught upon R is how much here? Look at here, R. That means R naught upon 4. Hope you are following. I'll cancel these two. Now that is equal to 2.303 upon 2.4 into 10 to the power of minus 3 into log of 4. Now log of 4 value is given 2.303 into log of 4 value is 0.6021 upon 2.4 into 10 to the power of minus 3. Children, if you simplify, look at here, T is equal to 1.386 upon 2.4 into 10 to the power of minus 3. Children, if you simplify these two, I'm going to get 0.575 or 578 into, so this will go to the numerator, 10 to the power of 3. In that case, it is 575 seconds. So T is equal to 575 seconds. That means 575 seconds are required to reduce the concentration of sewage from its initial concentration to 3/4 the concentration of HCOH. So this is how you need to solve this kind of numerical. Hope you understand that. Let me take up one more numerical for you. Children, let me take up the next numerical. The rate constant for first order reaction is 60 per second. How much time will it take to reduce the concentration of a reactant to 1/16th value? Given log 16 is equal to 1.2041. Remember, they may or may not give the log value, but you should know how to find out the log value by using the log table. Now let me solve this numerical. Solution. K value is given, that is 60 per second. Is it not? Now what do they say here? They say that the initial concentration will reduce to 1/16th. So I'll write, look at here, R is equal to R naught upon 16. Now you are supposed to find out T, time. So they are given one hint. What is that? First order. Now you know that first order K is equal to 2.303 upon T into log of R naught upon R. Is it not? Now what I supposed to find out? Time. So T is equal to 2.303. I'll take K here. The K value is 60 seconds per second. Log of R naught upon R is how much here? R is equal to R naught upon 16. R naught upon 16. I'll cancel this. Look at here. 2.303 upon 60 into log of 16. Log 16 value is given here. 2.303 upon 60 into log value of 16 is equal to 1.2041. Children, if you simplify this one, you are going to get 0.03803 into 3803 into 1.2041. Now if you simplify, 0.0462 second, or you can write t is equal to 4.62 into 10 to the power of minus 2 second. Children, let me take up the next numerical for you, which is very important for the board examination. This kind of a numerical has been asked in the previous years repeatedly. A first order reaction is a 20% complete in 10 minutes. Calculate the time for 75% completion of the reaction. Given log 1.25 is equal to 0.0969, log 4 is equal to 0.6021. Children, let me solve this numerical for you. Solution. Now first they say yes, a first order reaction. What I do? I write the first order reaction expression. K is equal to 2.303 upon T into log of R naught upon R. So R naught is initial concentration, R is concentration of reactant after time T. Now what they given here? T is given time, that is equal to 10 minutes. Now what I do? Let R naught initial concentration as A mole per liter. Is it not? If that is the case, then concentration of a reactant after 10 minutes would be R is equal to A minus A into 20%. So that is why I put here divided by 100. Now that is equal to 0.80A. If you simplify, you are going to get 0.80A. Now what else is given? That's all right. Now let me substitute all this value in this equation. Look at here, K is equal to 2.303 upon T is equal to 10 minutes, right? Log of R naught we have taken as A, is it not? R would be 0.80A. I'll cancel. Now 1 by 0.80 is equal to 1.25. 1.25. So that is why they are given the log value here 1.25. Look at here, 2.303 upon 10 into log of 1.25. Now children, look at here, if we simplify, you are going to get 0.2303 into log of 1.25 is equal to 0.0969, right? If they do not give also, you have to find out. Now that would be is equal to 0.0233 per minute rather, because it's a K value. So K value is equal to 0.0233 per minute. So you got K value here. Now let me take up the second part. Now children, look at here, calculate the time for 75% completion of the reaction. Now again, look at here, again let me consider R naught as A. Then R would be, what is that? A minus A into 75%, is it not? 75%. Now that would be is equal to how much? That would be is equal to 0.25A. You simplify, you will get that, right? Now I substitute here. Now what you are supposed to find out? T is equal to 2.303 upon K into log of R naught upon R. Is it not? Now look at here, T we are supposed to find a time. So 2.303, K value got it here, it is equal to 0.0233 per minute into log of R naught is equal to what? R naught is equal to, we have taken A, R is equal to 0.25A. I'll cancel this. Now look at here children, 1.0.25 is equal to 4. That is why they are given log 4 value here. Now look at here. Now if you simplify, this will be, okay, so 2.303 upon 0.0233 into log of 4. That will be 2.303 upon 0.0233 into log 4 value is equal to 0.6021. Now if you simplify, you are going to get, children, 62 minutes. So T is equal to 62 minutes. That means to reduce the concentration of a reactant by 75%, the time required is equal to 62 minutes. Hope you got it. Let me go for the next numerical of the same kind. Children, let me give some of the numerical for homework. Hope you will do it at your home. The rate constant for first order reaction is 60 per second. How much time will it take to reduce the concentration of the reactant to 1/10 of its initial value? Second one, a first order reaction takes 20 minutes for 25% decomposition. Calculate the time when 75% of the reaction will be completed. Third one, a first order reaction takes 23.1 minutes for 50% completion. Calculate the time required for 75% completion of this reaction. Fourth one, a first order reaction is 15% completed in 20 minutes. How much time will it take to complete 60%? Children, so these are the 4 numerical which have been asked in the previous board examination. Hope you can solve very easily, because these are just like the numericals which you have solved earlier.